there could be something underlying and simple, or it could be very complicated. Nature didn't ask my opinion.
What's up, you scholars of enlightenment? I hope you're having a wonderful day and have a wonderful Easter weekend planned. Physicists at Fermilab have just released a painstaking analysis of CDF2 experimental data that suggests that the mass of a fundamental subatomic particle of nature, the W boson, is slightly more massive than we would expect it to be, given the predictions of the standard model of particle physics and past experimental data. The result is the most precise measurement of the W boson mass ever produced, and is more precise than all previous measurements combined. Although the discrepancy between the W boson's predicted mass and this new measurement is tiny in absolute terms, it is incredibly statistically significant and represents the first conclusive experimental result that is at odds with the standard model. However, the result is in strong tension with measurements from other experiments such as ATLAS and LHCb at CERN, and came as a shock even to the Fermilab scientists themselves. The international particle physics community is now considering, debating, and checking the result. If the result is accurate, the implications for fundamental physics are enormous. Cracks in the standard model will help scientists to pinpoint where to look for new physics and potentially lead us to explanations for unknown phenomena such as dark matter, dark energy, and even the origins of the universe itself. To help us dig into this measurement, how it was made, its potential implications, and the road ahead, we welcome another fantastic special guest, Professor David Toback. Professor Toback is a professor of physics and astronomy and a member of the Mitchell Institute at Texas A&M University. His area of specialization is experimental particle physics and has focused on the search for new fundamental particles. This includes searches at the world's highest energy particle accelerators, such as the CDF experiment at Fermilab Tevatron and the CMS experiment at the Large Hadron Collider, or LHC, in Geneva, Switzerland. So who better to help us understand what is going on here? I guess we'll start at the start, Professor Toback. First question, what is the W boson and why is it so important? Because there's probably a lot of people out there who've never really heard of this damn thing and aren't really sure why it's so important to their everyday lives or why this result is such a potential crack in the foundations of particle physics. What is the W boson? Why is it so important?
That's a good question. The W boson it's one of the particles of the standard model. So over the years, we have come to understand that the stuff that we are made up of as human beings are made up of fundamental particles. So the atoms that make us are electrons going around protons and neutrons. Eventually, we figured out that protons and neutrons are made of quarks. But the things that hold them all together are what we call the force carriers, and those are the bosons, which you can see. That's as in Bose speakers, that's the family. So the thing that keeps the atom together, the electromagnetic force, is the photon. The thing that keeps the strong force together is the gluon. The W is less well known because it governs things that don't affect our everyday life as much. So, for example, why does radioactivity decay, right? Why do those things decay? How does the fusion that goes on in the sun work? And that's the W boson. So it's really important, and it really exists.
So I think if we have a little bit of a history lesson, it was theorized back in the 70s, I think, with the electroweak theory, and then discovered at CERN in the 1980s. So the Nobel Prize in 1984 went to Rubier and Vandermeer for discovering this force carrier, which is so important for radioactive decay. And as you say, the the processes that go on in the sun. So it's extremely important for us, even if we don't know too much about it. But why do we care about the mass? So what we found last week was that an experiment that you're with, CDF at the Tevatron over in the States near Chicago, posted this result that the W boson mass seems to be significantly higher than we would expect given the predictions of the standard model and previous data. So why do we care so much about the mass of this W boson? Why is it such an important thing for us to nail down and get as accurately as possible?
It's a good question. So our best understanding of nature and all of those interactions is the standard model. And the standard model is arguably the most powerful and well-tested description of nature ever conceived. It's remarkably good. It's incredible.
Yeah.
It predicted the W and the Z's existence,
Yeah.
which is one of the reasons we take it so seriously. But it's also based on fundamental things: the mass of the electron, the mass of the top quark, the Higgs. And it's not just that it says they should exist, but the model really holds together incredibly well. And it says, if our understanding is correct, the W has got to be this value.
Yeah.
Okay? It's really got to be this. And so what we did is we measured it. The question is the standard model correct? And the difference is tiny, to be sure.
Yeah.
Right. But the difference between the prediction and what we measured is hugely different.
Yeah.
Right. The analogy I kind of like is, okay, if I tell somebody to walk 20,000 steps to the edge of the cliff,
Yeah.
you know, it's a long distance. But if the answer is the cliff is in fact 19,998 feet away, you're going to get a very different outcome.
Yeah.
And that really matters.
Yeah.
So it means that something, either this measurement or our understanding, is really missing something. And that has huge implications.
So the mass of the W is sort of constrained, as we sort of see in some of these equations. People don't really need to know exactly the sort of underlying details, but basically all of these values in the standard models, the coupling strengths, the masses of various particles, the decay rates of certain particles, they all fit together. And if one of them is too far off, too out of bounds, it sort of has a knock-on effect in all the other things that we observe, doesn't it? So they all have to fit together in a neat, I think they call it the electroweak fit. And if one of them is too far off, it sort of breaks the whole model. They all constrain one another.
Yeah, the equations you've got there are nice and pretty, right? They're still, let's be clear, they make most of our eyes glaze over when we see equations.
Yeah.
But that's the simplest version. I mean, the sophistication, pages and pages and pages of calculations that you can't even write down. You need computers to calculate them.
Yeah.
But you got it right. If one piece is off, look, it's like if you're trying to solve a case of a murder, right? If one fact doesn't fit, you can't convict. It's just, it matters.
Yeah. Are these cracks, I guess, if this is a crack that holds up, this is showing us potentially the places that we might go to look for the flaws in the standard model, right? So it's very useful for theorists to know where those little misalignments, where those little discrepancies might be hiding, because it can give us little hints as to where we might go looking for beyond standard model physics, right? Because we know the standard model can't be the final word on particle physics. As successful as you very eruditely said it has been for the last 50 years, it can't explain things like dark matter, like dark energy. It's got a lot of inputs that we have to put in by hand. So we know that there's more physics to find. It's just the standard model has held up incredibly well. So we want to find those little cracks to go through, don't we?
Yeah, exactly. Look, Newtonian physics, Newton came up with this in the 1600s, and it's magnificent. It tells us how to build roads and skyscrapers. but it's a terrible approximation. If you care about things like the speed of light, right? It's got nothing for the speed of light. So it's got to be wrong. Is it good enough for, building bridges? Yeah. But the standard model is good enough for describing what we know, but it's not good enough to explain everything. As you said, doesn't have dark energy, doesn't have dark matter. Heck, it doesn't even include gravity. So
we don't talk about gravity, Dave. We don't talk about it. That's over there somewhere. We don't worry about that.
As a scientist, I care about that. It matters. So we know it's got to be incomplete. And what this is, as you said, the hope is that this might provide us a clue as to the right way to go. And as an experimentalist, to quote your countryman Sherlock Holmes, we must find theories to suit facts, not facts to suit theories. And we're in the business of facts.
Exactly right. So getting into the sort of specifics of the work that is done at Fermilab, and particularly for this experiment. So we want to study W bosons. We want to determine their mass. So we obviously have to produce them, and then we have to identify them. So let's start with producing them. So how do we go about producing these things and getting enough of these things to do a kind of statistical analysis on their mass? How do we do that at Fermilab?
All right. So in many ways, the experiment is the same ones that that helped discover the W and the Z in the first place. The big issue is you have really big particle accelerators, Fermilab. You take a proton and an antiproton and you bash them together. E equals mc squared, one of the few equations people are comfortable with. And if you've got enough energy, you can make enough mass and you can make a W. And so the idea is that you can produce the W, and then you surround it with an enormous and powerful detector.
I think I've got a beautiful picture building here, I think.
Yeah. Hopefully there's a picture of somebody in that. I mean, that's a ginormous thing.
Down at the bottom here, I think.
And so you put that around the W, and the W doesn't live very long. 10 to the minus 24 seconds. It decays into stuff. And then you can measure the stuff with incredible precision in the detector. And so in some sense, a decent analogy I like is, let's say you wanted to measure a drop of water. Okay. So if I knew exactly how high I dropped it from, right, it hits the ground and it spatters a little bit. And so if you look at how far things spatter, you can figure out how much the drop weighed. And the more sophisticated you are in able to measuring that, the better you're going to do. You got a really sensitive location of where all the drops go, that helps. But if you can measure each and every drop, you can do well. And if you can use things like conservation of momentum, you can see if you missed a drop and correct for that. That's the kind of stuff that we do.
So this is the and you really nicely explained that. So we smash these protons and antiprotons together. We can produce these W bosons. As you said, they don't live very, very long, and they decay away to different particles. And we can see these signals in our detector. So the one that we look at in this particular analysis is the W boson decays to an electron or a muon and a neutrino. So we see this beautiful electron or muon track, and then sort of nothing going in the opposite direction because this neutrino is essentially invisible, punches through our detector. But we can see these beautiful signals that the W must have been there in the past. So it's a kind of backwards looking detective drama where we're putting together all those little clues that we see in our detector, all of these little signals to know that the W must have been there. And then you very nicely explained it, that from these are the sort of plots that you were talking about. Given what we see in those drops, those electrons and those neutrinos, how they behave, they're what we call their kinematic distributions, we can tell how big the sort of pool of energy that was the W must have been to produce these distributions. Is that a fair characterization?
Yeah, right. It's E equals mc squared going the other way. right? So you need a lot of energy to produce the mass of the W, and then the W decays, and you get the energy out again. So if you measure the energies out, you can measure the mass of the W. That's exactly right.
So this is basically a sort of a model fit, if you will, where you sort of you take a model of what you think you should get in terms of the distributions of the momentum of the electron and the neutrino, and you sort of fit what is the best W boson mass to give the data that you see. Is that correct?
Yeah, right. I mean, one of the things that it's hard to see on this slide is what that's doing is counting the number of W's that look like that.
Yeah.
And that's thousands. And it's also hard to see that there are both points, which is our data, and a line, which is the prediction.
Yeah.
And you can't see the difference.
Yeah. That's always a good thing, by the way.
It's a good thing. It's a good thing.
So what, I mean, I guess I can sort of think of some reasons why this is so difficult. First of all, you have to have a very good understanding of fundamental physics, right? To predict from first principles with a model what these distributions, quote unquote, should be. So you have to have a very good simulation of physics. And then you also, I guess, these distributions that you see in your detector are the real distributions of the particles, but sort of convolved with a detector response. So just like what we see outside is sort of modulated by the kit we use, a camera or our eyes or whatever it might be, these distributions are the real distribution that actually exists in nature, but with a little bit of a sort of smearing added onto it by what our detector sees. So I guess you have to have a really good understanding of nature up front to do this modeling. And then also, I guess you really have to get to grips with the underlying behavior of your detector. Is that?
Absolutely. How well does the detector behave? Is it the same in all directions? Right? Has it fallen a little bit? Has it twisted a little bit? Did it get humid and it's wobbling? Absolutely. All of those things we worry about. We worry about them a lot.
I think
the nice thing is that we've got huge numbers of collisions, so we can check that stuff with things that aren't W's.
Yes.
So we have some confidence that when we measure the W's, that we can trust the data.
So I think if we look in the sort of paper, you can see the horrendous number of systematic errors that could possibly, or systematic uncertainties that come into this measurement. So you can think about, you have to make sure that you measure the momentum of these particles absolutely correctly so you can infer the W boson mass. Does your magnetic...
These are only the big ones.
These are...
These are only the big ones.
So these are ones like, for example, so to measure the momentum of a charged particle, we send it through a magnetic field. It curves in the magnetic field. Now, do you know exactly what your magnetic field was? Do you know exactly where the pixels were that gave you the curvature of that track? These are all things that we have to dial down perfectly. My favorite one of these is, do you actually know the energy that you smash the quarks and the protons together at? Because actually they're jiggling around a little bit inside the proton as well, aren't they? So this is these parton distributions. So there's so many little things that go into this measurement. It's an incredibly difficult measurement to make.
Yes. So for us, in principle, we need to know the actual energies of the quarks to get the distributions right. But to measure an individual W, you can use special relativity to get back to the mass. But yes, we agree.
And then I guess we've got also, did your particles lose some synchrotron radiation before they got to your detector? It's just an incredibly difficult modeling and then detector nailing down that you have to do. So I guess does that give us some understanding of why this result has taken such a long time? Obviously.
Oh yeah. So people have been measuring the W for years. It's not hard to get it approximately right.
Yeah.
Right. The analogy that I like to use, and okay, I'm in the US, so it's like you're measuring an 800-pound gorilla to an ounce and a half.
Yeah.
So for the folks in the metric system, a 400-kilogram gorilla to
Yeah.
0.05 grams.
Yeah.
Okay, that doing it approximately right is not hard, but getting it time, it just takes a long time. It just takes a long time.
I've heard a couple of analogies actually from people who worked on this at Atlas, and they said it took them 5 years to get their first measurement out on this W boson mass. They said things like even the fact that the protons don't hit perfectly head on, there's a very, 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 very tiny angle between them, has an impact on this data. All kinds of, even as you sort of alluded to, the slight sagging of the detector under its own mass, or the heating and cooling of it that very slightly changes its alignment. All of these things can feed into that W boson mass measurement, and understanding how they change, understanding what they do to the results so that you can remove those effects. It's an absolutely incredible amount of work that's been done, and the level at which these CDF scientists understand their own detector is absolutely phenomenal.
We're proud of that. We're proud of that.
You really should be. It really is an amazing amount of work. So I guess that there's one sort of elephant in the room, or maybe we should say gorilla in the room, given your last analogy, is that this result, as amazing as it is in tension with some other results that we've had in the past on this same measurement. So this is a plot that was made. It's unofficial, but it was made by a former colleague of mine on LHCb, Will Barter. And I
was going to say, it's good to see our LHCb colleagues well represented there. I'm very pleased to see that.
Exactly, it popped up on my Twitter feed because he's a former colleague. So that's the bias here that I will admit.
I'm cool.
But
we're all on the same team. Whether
exactly.
we feel that way or not. Sometimes
there's no subversion here. There's no spying. I just want to get to the bottom of it. So he put these all on one graph, so you can see the previous measurements of this from previous experiments, Aleph and Delphi and Opal, even D0. That's a question that I wanted to ask you first up. Actually, at Tevatron, there was D0 as well as CDF. Is there any anticipation of a D0 result on the W boson mass, or is that not something that we would expect to see?
Unfortunately, the answer is no.
Okay.
I was actually on D0. Gorgeous experiment. Fermilab did such an amazing job of delivering high luminosity that it beat up the inner parts of their tracker. So they're just not going to be able to produce a measurement with a high enough precision to have been worth it. So it's a great loss because it's an amazing detector, but it's not coming.
That's a shame. It would have been nice to see if they
Absolutely
saw a similar thing for a similar collider. That is a real shame. But regardless, so we'll put these all on the same plot, and we can see that there is a little bit of a tension. So the other ones seem to be consistent with the standard model. So the standard model prediction is sort of in this black line with the sort of grey bands around it. And you can see the previous ones, obviously they have higher errors than the new CDF result, which has much smaller systematics and statistical errors. But they're more or less consistent with one another and consistent with the standard model. Whereas the CDF one is obviously something new. It's 7 sigma away from the standard model. What are we to make of this tension? Is it simply a fact of saying to the other ones, get your errors down, bro, and then we'll talk, or what are we to say about this?
Okay.
I know this is slightly tricky politically.
No, you're asking the right question. You should ask, hey, this is the data. What should I make of it?
Yeah.
And that's the right question. There are a couple of things that I think are worth pointing out. The first is that the error bars are big.
Yep.
And we need to be careful of our biases right? Because our eye is biased
Yeah.
by the line,
Yeah.
right?
Yeah.
Right? You know, I can do silly things and count the number of points above the line
Yeah.
and the number below the line,
Yeah.
but I don't know that I've done anything useful.
Yeah. When you know what it should be, it's very easy to try and put them on the line, isn't it? When you know
Yeah.
what you think it should be.
Yeah. So I look again. I don't want to be in the business of what it should be.
Yeah.
What I want to do is be in the business of what we measure,
what it is. Yeah.
and I want to be in the business of what other people measure, because I take that very seriously. And people in science have this idea, or people outside of science, I should say, have this idea that these guys got it right or these guys got it right.
Yeah.
And in science, that's just not how we do things. Sometimes it's not or, it's and, right? It might be that we're both right. I mean, Einstein did this kind of thing with relativity. It may be that we're both measuring the W, but we're measuring different things about the W and we don't realize it. And in fact, this could be even more interesting rather than something that we should fight about who got it right.
Yeah.
I take that very seriously. You know, as an experimentalist, what I want is more data. I'm really looking forward to Atlas and LHCb giving updated results. I'm looking forward to CMS having a result.
Yeah.
Are they different? Yeah. On the other hand, the statistics there doesn't.
Yeah.
The difference between us and the other experiments is much smaller than CDF and the standard model. That's a statistical statement.
Yeah. Yes, that's very true as well. So we'll have to wait to see when they shrink their error bars down to the CDF level if we still have such a tension, or whether such tension disappears a little bit. And that raises a question, actually. Why are we seeing the result here from CDF first ahead of those other? You would expect naively that LHCb, Atlas, especially CMS, with their higher luminosity, higher energy, might be able to produce these W bosons quicker. Is this just a temporal thing where this analysis has been going longer for CDF, or does CDF have certain advantages for producing W bosons we can look at?
Yeah, we do have some advantages. In some sense, it is temporal. It's just a matter of time. I mean, there are certain. I never bet against LHC folks. They're very creative. I don't see LHC as better or worse. They're just different. They've got huge advantages in some ways and disadvantages in the others. So let me give you an analogy that kind of works for me. And you can tell I probably watch too many crime shows here.
No, it's good.
So one of the things at Fermilab that's very useful is we have lower energy. And that sounds like a disadvantage. But one of the advantages of lower energy is that you produce the W much closer to at rest. And so you can say, well, why would that be an advantage? And before I start the comparison with the LHC, it's got huge energy. And so it's going to produce lots of Ws. It's going to produce Ws more often. But there's going to be so much energy left over that the W is often going to get spit out pretty quick. So I like the idea of surveillance cameras for trying to measure things. So if I've got a suspect and he stops and he stares at the camera, I'm going to get a really good picture for facial recognition. If I compare that with, dozens or hundreds of spottings as he runs through the streets of London at high speed with lots of other people on the street, it could be that with enough measurements, I'm going to do just as well, if not better. It's not that one way is better than the other. They're just different and they have different advantages. So we produce fewer Ws than the LHC. They produce huge amounts, but ours are at rest. So we can get a much better look per W.
Yep.
At the LHC, they're producing lots of collisions at the same time. You got to pick out the one that was the W.
Yep.
And that W is moving very fast. So it's just, there's a lot of other stuff you got to take into account, and that's hard.
I think they mentioned from a more technical perspective something that people might find a little bit more difficult to understand, but they were saying because of that lower energy as well, the parton distributions, how those quarks and gluons are wiggling around inside the proton, are more well understood at those lower energies than they are, for example, for the LHC. So naively you would think, oh, I produce more, as you say, this is great, we can do the analysis quicker. But if you're not producing things that are easy to look at, easy to resolve, it's incredibly high luminosity and messy, sometimes that can be a disadvantage. I think they even did some low luminosity LHC runs to be able to look at this better. So it's not always an advantage to be the highest energy or the highest luminosity. It's
look,
more to
their detectors are finely machined, much newer. They're gorgeous. Man, I wish I had those detectors for CDF. But yeah, the other thing is that as they get more W's and Z's and top quarks, they're going to be able to understand the parton distribution functions, and the errors will come down. Like I said, I'm never going to bet against these guys. It just takes a long time to get all of this stuff done right.
Yeah, and there's no. I hopefully it's coming through clearly to everyone who's watching. It should be. There's no slight or any insinuation on any group of these physicists. We're all on the same team. We're all working towards the same idea. There's no suggestion that anyone's done anything wrong or is being too.
You can suggest it's wrong. We just don't think so.
We can all suggest it's wrong as long as we then look and work out if it's wrong afterwards. But no, there's
let the science talk.
Exactly right. There's no insinuation that there's anything underhanded going on, even if I have my LHCb hat on. So yes,
you're allowed.
So I guess that brings us on to the final question that I had for you, David, which is if this measurement holds up, and I know you're an experimentalist like myself, so maybe we're treading into grounds which you probably know a lot more about this, the theory of this than I do. But if this measurement holds up, are there any potential explanations? I know there will be an explosion on arXiv of theorists putting out papers to try and explain this discrepancy, but are there any sort of leading ideas or extensions to the standard model that could potentially explain this discrepancy, or do we just have to wait and see? I've seen people jumping out with all sorts of things, compositeness and new scalar fields, which is always the answer, and Susie never dies, it always comes back and tries to save the day. So I've heard all sorts of things. Any ideas as to what we could be looking at if this is the real W boson mass?
Look, you hit you got it right. There are lots and lots of papers already from people who said, hey, if it were higher, my theory says this. If it were lower, my theory says this. So there's no shortage of theories already out there. And I think your read of the history is correct that we will get lots of new ones as well.
It's always the same from being in HEP. As soon as there's a discrepancy, I remember we had a 3 sigma deviation in CP violation in demixing, and then papers just went woof, like over the next sort of couple of weeks, couple of months, which, you know, as they should do, which we want to try and understand these things. But yeah, there's all sorts of things go up, and obviously they can't all be correct.
Yeah, I think good is going to come from this. You know, the dominant issue to me is from asking the theoretical question, is the standard model prediction correct? I mean, the uncertainties are incredibly low, but we are learning stuff all the time. We've got new data from the LHC, which could potentially shed even more precision. Okay, I need one of those. That's kind of cool.
Yeah, it's kind of cool, isn't it? Somebody stuck the crack on there, but I like what they've done. Yeah, they are.
Yeah. Favorite theory? Yeah, I'm just not in the business of favorites. Some of those theories I find very compelling. To use the technical jargon, it's degenerate. once you have lots of things which predict the new thing that showed up, you say, okay, well, what else do you predict? Let's go take a look.
Well, a lot of these things, as you'll be aware, is they all have a sort of lowest mass stable state, which always turns out to be a dark matter candidate. That seems to be like you have to have that nowadays to. I remember all of these papers throwing out that explain X, Y, and Z and have a dark matter candidate. So like you say, it's important to kind of accumulate more and more of these discrepancies, more and more of these cracks, isn't it? Because the theory that you put in hopefully will not only explain this W boson mass discrepancy, but maybe other things that we also want to explain. And then we're starting to really get a crowbar underneath where these cracks in the standard model might appear.
Yeah, I think that's right. I keep coming back to crime shows, right? Sometimes it's individual murders and sometimes it's a serial killer.
Yeah.
Right. And if it's a serial killer, it means that you can put the crimes together and that you can combine the clues and that gives you a hint.
Yeah.
Sometimes they're not related and it's not obvious. Dark matter is clearly a thing. Is this going to point the way to dark matter? It's not obvious to me. It's just not obvious.
But it's never obvious until after you've discovered it.
Nature is remarkably stingy with her secrets.
Yeah.
She's remarkably stingy with her secrets. The world we live in it's not simple. Every now and then, you look at the periodic table and, you see this crazy looking complexity. And when you understand it, you can say, I could have, instead of calling it hydrogen, helium, lithium, I could have just called it 1 proton, 2 protons, 3 protons, and it makes sense. And a lot of us have looked at the standard model and said, who needs 6 quarks? Why so many? There could be something underlying and simple, or it could be very complicated. Nature didn't ask my opinion. On the other hand, I happen to like this universe that seems to have done a remarkably good job of allowing me to exist and get to do science.
Yeah, so I guess we'll just have to wait and see. We'll have to wait and see where those cracks appear. We'll have to wait and see if this crack holds up as we see more data from LHC and. But yeah, fascinating result. Hell of a lot of work that went into it. An amazing result for an amazing group of scientists. And I'm excited to see where we go from here. Dave, thank you so much for taking the time to have a chat with me today. I really, really appreciate it. I know you must be extremely, extremely busy with everything that's going on.
It's been a lot of fun. Thank you. Stay bad, my friend.
I certainly will do that. Dave, where should people go to find out more about what's going on with this result and keep up to date with what's going on with the W boson mass and maybe more of what's coming from the excellent scientists at CDF?
So the best place to go these days is cdf.fnal.gov.
I will send people there. The links to Dave's work and that website will be down in the description. So if you want to find out more about this amazing discovery, head over there and you can find out more. Next week, we're also going to be talking to a theorist who will give some ideas about maybe where this leads. So we'll let his imagination run riot. So we're going to do a little bit more follow up on this. But Dave, thank you so much again for taking the time. I've really enjoyed it. I've learned a lot. And when we find out more on this, let's get you back and let's have another chat.
Sounds good, my friend.
Take care, buddy. Have a wonderful afternoon, and let's talk again soon.
Thanks a lot.
Bye, buddy.
Right, bye-bye.
Bye now.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.